So I'm going to be talking about more trying to figure out, in a very microscopic sense, what electrons are doing when they are on the same uranium atom in uranium, ruthenium, silicon. Are they entangled, forming the sort of J equals 4 movement that people have been talking about? How itinerant are they? And what sort of crystal field states might they be occupying? I will address that, but not as directly addressing what the hidden order parameter is going to be as the last time. So if you look closely, for those of you who have looked at these affiliations, you will know that I'm here from the future. Shortly after Bernie Sanders stepped into office, he dramatically stepped up funding for the sciences and time travel was developed. I just hope my coming back hasn't somehow changed these future events. But now, the Center for Quantum Phenomena in the NYU Physics Department is going to be inaugurated, I believe, early next year. We're currently looking for 2 faculty hires in this coming in the fall. So I just want to highlight that before moving on. And these are some people in my group. All of them have contributed to this to some extent, but I want to particularly highlight Wray, the graduate student who's been focused most on these projects, and our postdoc team now. And in the talk, I'm going to start by introducing the spectroscopies a little bit because we haven't really had X-ray absorption in RIGS yet. And I'm going to look at an application of these spectroscopies because I'm focused on X-ray absorption in RIGS performed with very low energy photons in the vacuum ultraviolet, not actually the X-ray regime. And that changes things. So I'm going to take a quick look at what that means for some of our measurements on samarium hexaboride, the kinds of things that we can get in a system that, from the perspective I'll be coming from, is simpler than uranium, ruthenium, silicon. And then I'll plunge into what we can see in uranium, ruthenium, silicon and try to extract some concise conclusions. And if there's time, we'll talk about a new synthesis and spectroscopy facility that we have at NYU. So, in X-ray absorption spectroscopy, we have a photon coming in tuned to the binding energy of some core electron. And I got this animation from Wan Li Yang at the Advanced Light Source, by the way. I really like it, but I should give credit. So you promote a core electron up to the valence level. The electron sticks around is usually the way it works, at least we think about states in which it sticks around. And what you're left with, especially if there's angular momentum in the core level, if it's not an S symmetry core level, you're left with something where the valence electrons are strongly entangled, or can be strongly entangled with the core electron symmetry, and you, as a function of incident energy, you probe different states that represent how the symmetry of the valence electrons projects onto these core valence entangled states. So you get sort of a fingerprint of the valence electron symmetries on the site that you're scattering from. And it seems horrendously complicated to have to incorporate the symmetry of the core hole in everything. Actually, it makes things simpler because the core valence interaction can have an energy scale of 10 or 20 electron volts where I'll be looking, which means it can dominate all the low energy physics that we're concerned about. You're just taking a projection from a complicated ground state onto a simple intermediate state. Anyway, the way we actually determine what the absorption coefficient is to, so when some electron decays back down to fill the core hole, we see the secondary Auger electrons that come out. Actually, to some extent, it's not, so we measure the sample to ground current. It's not just the secondary Auger electrons. Those have a high energy and a short mean-free path. If they're coming from a little deeper in the crystal, you can get a cascade of, well, I shouldn't say secondaries, with the Auger electrons, and then you can get a cascade of secondaries from their inelastic scattering off of other stuff. So we count all of these potentially multiply scattered electrons. It gives us a penetration depth that's maybe on the order of 1.5 nanometers, a little deeper than photoemission spectroscopy typically would be, but not by very much for X-ray absorption For rigs, we measure the much rarer case where an electron decays back down, and instead of kicking out an electron, it kicks out a photon. So with rigs, we have the power to see low energy excitations in the material. We can see, for example, what degrees of freedom are gapped out of the local energetics. And rigs is going to come in the second half of the talk to sort of help fill in the picture of what degrees of freedom are really in play for him. So, like I said, I'll start with an example on samarium hexaboride. I'm not going to do it justice because this, in the introduction, because this is just an example. But samarium hexaboride, as I think of it, is a material where you have one samarium atom per unit cell, and the boron dresses things but doesn't matter all that much. You have essentially a cubic lattice. And Zero and Pierce Coleman and I believe a couple of other people in 2010 showed that when you have that kind of scenario, when you have a single F electron element per unit cell, it's very easy to get a topological insulating state. All you need is, in this picture comes from a 2013 PRL where Lou et al. Showed that this is actually very plausible and should happen for samarium hexaboride. All you need is for there to be a bunch of for the F electron states to be at the Fermi level and sort of nominally filled. And then D electron states up here that are highly dispersive, one of them comes down below the Fermi level at just one high symmetry point. And this turns out to intrinsically be a topological band inversion that gives you a topological insulating state if the electron band, F electron band is circled here. And that's really exciting. More recently, a bunch of ARPAS studies have suggested that this really, and transport have suggested that this really is a topological condo insulator. One could call it the first one. More recently, Nakajima et al., the Paglioni group, has shown that the surface seems to be ferromagnetic in a patchy way. And when you have ferromagnetism at the surface of a topological insulator, domain boundaries have intrinsic one-directional ballistic conduction channels, which is what Paglioni is measuring having sort of quantized transport steps here. It's a scenario that people have been working towards for a long time, and to find it intrinsically maybe at the surface of samarium hexaboride. You need some more experimental confirmation, but it's very exciting. It means you don't need to mess around too much with the system to get this scenario. We've been looking at this, and again, our spectroscopies are sensitive to what's going on at the surface, so we're sort of specifically interrogating the environment that Paglioni was looking at. And these are X-ray absorption measurements on samarium hexaboride at what we're doing is promoting a 4D electron to the 4F level. These are the incident energies. We're sort of just outside of the soft observation, you could say. And you see a whole bunch of features. Dark blue is 20 Kelvin. We're cycling quickly up to high temperature, which sort of this black curve represents what happens after you quickly heat it up to 300 Kelvin. The spectrum changes quite a lot. In fact, in the low energy region with all this detail, sort of nothing is the same. If you take different spectra where we subtract what do the higher temperature spectra look like when you subtract the low temperature spectrum, what's changed, you find that features that a multiplet calculation associates with no local magnetic moment, with 6F electrons and no local moment, lose intensity, and features that the calculation associates with, in a condo lattice picture, sort of a spin one, a local degree of freedom, a large moment. In valence terms, it would be tentatively associated with 5F electrons being there. They gain intensity as the surface ages. And that's just what you want to get magnetism, really. If I said, let me ruin this condo lattice and turn it magnetic, I would say, okay, I'm going to change it to introduce a whole bunch of large moment sites, and that should do the trick. Get rid of, anyway. So So our measurement, if we try to sort of algebraically extrapolate what the original, from the experiment, the large moment and small moment curves are, we get things that look like this with shaded error bars. And we get a trend from there being sort of something with a tendency for moments to be small or sort of singly screened to a tendency to have large moments. And luckily, some people with a valence-sensitive technique, a photo emission technique that sort of determines valence in the circles, Zach Fisk's group have recently also identified valence changes of the surface. And this is sort of interesting in contrast, and it's something I want to highlight about the technique that I'm applying before we get into uranium, ruthenium, silicon. They see that valence starts from about 2.5 F electrons per samarium atom and progresses to 2.7. We see that there are something like 0.3 to 0.4 large moment sites in the pristine condition, which would correspond to something like 2.3 or 2.4, it would correspond to, 2.3 or 2.4 plus valence in their scenario if valence were determining the local moment. So I just want to highlight that our technique is sensitive to local moments and to coherent states, but it's not sensitive to charge density in F orbitals. This sort of thing isn't an inconsistency between measurements. In fact, if you take non-insulators, our technique will say our technique will say that there's sort of integer valence. There's a certain number of degrees of freedom per site in the non-insulator, where valence-sensitive measurements will say actually it deviates from integer valence because they don't see electrons that are coherently there but live on ligands. So, all right, with all that, we've talked about the technique, we've talked about samarium hexaboride. Uranium, ruthenium, silicon has a lot of open questions, and there's a lot of previous literature sort of that kind of contradicts itself in terms of interpretation of how we should look at the material. I'm not going to parse all of that because to some extent it's already been parsed earlier. In fact, let me skip even this introduction. But I do want to highlight that sort of the theoretical perspectives that I've seen most where people get at this are either based on density functional theory, which is great because it's coming from first principles, and this is a very complicated system, so it's very helpful to have to not have to rely purely on your intuition. And that's predicted things like rank 5 pneumatic order, Uriah quanticle. That's where I learned the word Uriah quanticle before I started looking at NIXS studies that we'll hear about tomorrow, or this another case of, anyway. So the issue with DFT pictures that you want to see bands, and ARPIS doesn't show bands very nicely here. This is an arbitrarily chosen set of ARPIS images. I've also done ARPIS on this material, but you see this is momentum versus momentum, constant energy in each of these images. You see these very, very broad things where features are sort of broad on the size scale of the Brion zone. And that says to me that you need some sort of local picture to understand what's going on. And probably accuracy. So the opposite starting point is what we've heard about a lot this morning to come from a crystal field perspective. And that's great because there are a lot of scenarios that can give you something that has small susceptibility in hidden order state and large susceptibility just as you leave hidden order. If you have a singlet round state or many body coherence giving you, and the icing anisotropy is also very easy to get from the crystal field scenario that we have here. But here again, there are some real-world questions with, for example, crystal field excitations haven't been definitively identified. And if you want to say that there's a crystal field hierarchy, that's the habeas corpus. Neutron scattering has been used extensively to look for them. Also, just in terms of this picture from a theoretical standpoint, it's hard to interface this highly local standpoint with with realistic many-body models. There are extra steps that need to go in. So you end up stepping into a lot more complexity as you do that. And the attribution of 5F2 as the starting point, as the common starting point for discussions today. Should it be the ground state of 5F2, which has a J equals 4 angular momentum? Should that be the state manifold that we have to work with? That's a very open question. Studies by Jeffries and a very recent paper by Jason Jeffries, a very recent paper by Corwin Booth, that both suggested that valence is actually closer to radium 3 plus 5F3. So I'll address mostly points 1 and 3. Yes, I don't have much ambition beyond that. And the last thing is that there's interesting Kondo coherence that has complex temperature dependence, and again, that's been discussed extensively. So at the end of the day, you kind of have a blank slate if you are approaching this as a theorist. You can start from an itinerant picture with J equals 5 halves single electron bands being the basis of your physics. You can start from a local picture, probably with J equals 4 2 electron entangled states on uranium. They're intrinsically, you get different numbers of degrees of freedom for 2 electrons on a site from these starting points. And reading through the theoretical literature, I personally have had trouble converging on something where I was able to put my finger down and say, I believe this. And this actually takes us really to the starting point of where I was at when I got into investigating this. So, so the reason this material was highlighted, this material came up in discussions when we were talking about what we should do. I was based at the Advanced Light Source when I started studying this, and had a connection with the Merlin beamline, which is the only beamline the only really active beamline specialized in RIGS and XAS in the vacuum ultraviolet, these very low photon energies that you need for this material. And in 2014, Frank de Groot and Christina Kvashnina put out a paper that I love the title of, Invisible Structures in the X-ray Absorption Spectra of Actinides, where the punchline of the paper is, if you measure actinides, well, specifically uranium compounds in the examples they were drawn, with any kind of X-ray resonance other than the vacuum ultraviolet O edge, then you will just get a single featureless peak. And if that sounds perfect, then, well, that's the way it sounded to us. So we thought, aha, we have a vacuum ultraviolet resonance that we can explore. We can see a bunch of structure. This is in relative incident energy versus intensity and X-ray absorption. And we can see a bunch of structure and try to analyze it, where there have been a bunch of higher energy studies, but they haven't been able to see structure. The reason for this is that the core valence multipolar interactions, which split states by symmetry, that will let you discern the symmetry of the valence electrons, they're very large for the O edge. And the orbital lifetime, inverse lifetime, is very small for the lifetime broadening. Where at the other edges, the inverse lifetime broadening is large and these interactions are small. So, this is what the spectra look like. Experimentally, if we cleave uranium, ruthenium, silicon in vacuum, we get an XAS spectrum that looks like this. If we expose it to air, we get a spectrum that looks kind of similar, that has bulges in funny places. And if we do multiple simulations for various 5F1, 5F2, 5F3 ground states, we see a qualitative correspondence with 5F2, where you can kind of line up this feature and this feature, and maybe there's a hump in here. And we don't see a good correspondence with 5F3, where there's a local maximum around here, where there's a local minimum in the 5F2 spectrum in the experimental spectrum. So without knowing very much, we started thinking, it looks sort of like 5F2. Then we took a second derivative, and the oxidized surface had a pretty good one-to-one correspondence between if there's a feature in the second derivative at the surface of the oxidized feature surface, then there's a feature there in the 5F2 simulation and vice versa, and we couldn't find the 5F3 features. So this suggested to us that the coherent state looks 5F2-like, and then there's a one-to-one correspondence between the oxidized surface and the pristine surface. It's just a little bit, the intensities are a little bit weaker for some features and change for different features, which suggests that there's itinerancy playing a role and changing symmetries locally. So we have had the great privilege recently to perform, I see smiles, someone's really high, to perform measurements on a wide range of different chemistries. These are samples that have been developed by former students and students of students of Brian Maple. We've been in particular contact with Nick Butch, Andrew Gallagher, and Ryan Baumbach for this really interesting phosphorus dope sample, which is electron dope. And Sheng Ran just got us the iron and arsenic dope samples. And all I want to point out is there's actually a lot to say about this, and I'm going to say very little because we just got the data in the last month, and I'm still parsing exactly what I should say. In the lowest order expectation from like an Anderson model, you would expect the leading edge of resonance to shift this way, down in energy, as you electron dope, like with this phosphorus dope sample, and up in energy as you oxidize the surface, like with the oxygen exposure rhenium dope sample. And we see that, but even for samples that don't have a nominal doping, like iron or osmium, we see shifts relative to the pristine surface. So that was the source of my question: are electrons being pushed around as you dope into this? Because again, it is very, very electron rich. You're trying to squeeze as many electrons as you can on each element, and that's going to be a different number for different ones. So there's a lot to say about the various ground states that these get to, and I will say a little bit more about that later. But what I do want to highlight here is that no matter what, we have the feature, even when you go to a very electron-doped case, you can still see all the features for a 5F2 J equals 4 local state. And the 5F3 ground state doesn't really jump out at you. The features become more and more broad, and of course they shift, but they really follow the pattern that you expect for the local degree of freedom staying J equals 4 length. And again, you can actually dope 35% of the electron for itself. Dichroism is something that we'll hear exciting things about tomorrow. It's something that we got into because, in particular, looking at simple crystal field models, we saw that there was, we are looking at a dipole matrix element, and all of the different crystal field ground states proposed in a crystal field picture have different intrinsic dichroic amplitudes. Now this is just amplitude. Actually, it's the same features no matter what. Here's a simulation of the features. Here are the features that we actually see. You can see sort of, this is in the more detailed lower energy region of the XAS spectrum. You get a pretty good correspondence. It seems like we're getting the right symmetries anyway. And so again, it's only the amplitude that changes as you go between different crystal field states. The fingerprint, where the features are, doesn't change. And that's a distressing situation to be in with a spectroscopy like this, because amplitude is directly corrected by itinerancy. And we don't really, we can take something from it. So we have this amplitude that's kind of in line with the gamma 5 state. This shaded region is where we expect amplitude to be for gamma 5. But more to the point, if I say that the ground state is a singlet and at higher energy you have a doublet, which is what people usually the picture people usually appeal to have large susceptibility outside of hidden order and small susceptibility inside hidden order, then I'm going to expect a very large change with temperature in dichroism if I say that the pseudospin is free when you leave hidden order. And we don't see that. We see dichroism stays flat. It doesn't. So gamma 1 is also plausible with our measurement, especially if you change the internal mixing parameters for gamma 1. But we don't see this temperature dependence going up to gamma 1, gamma 2. Now, to not make too much of a point of this, this is something that's very significant specifically with respect to crystal field models. But if you have a lot of itinerancy, or if you have a more complicated starting point, this may not answer a question for you. When I brought this up with Gabby Kotlier, he said, yes, that's very interesting, it's certainly relevant, but I don't know what that's going to do to the picture from EMFT just yet. It's going to. So I don't want to say that when you incorporate itinerancy, this is necessarily ruling things out, but it is constraining what the local pseudospin looks like. If you say that you have a crystal field like pseudospin, what sorts of, how free is it really? So you could have, gamma 5 has no intrinsic temperature dependence for dichroism. You could have a true free gamma 5 pseudospin, or you could have a gamma 1 pseudospin that's not free, that isn't allowed to access 4 pi in pseudospin space. We wanted to play with that a little bit more, so we also used iron doping to take this into the large moment antiferromagnetic state. Now the beauty of this is that we can rotate the pseudospin to a new axis for the ground state. In all of these pseudospin pictures, you can account for both hidden order and large moment antiferromagnetism. It's just you need to take pseudospin from the specific axis is different. The axial change is different for different spins. For gamma 1, it could be you're taking it from the sigma z axis to an in-plane orientation, the sigma x axis. And in that case, again, for gamma 1, gamma 2, the large moment magnetic state should have large dichroism. And we don't see that. This is our measurement. Dichroism is on this axis. I've overlaid it very roughly on something from Shunran and Maple's recent paper showing the phase diagram with iron doping. And we see this maybe very small increase in dichroic amplitude, but that can be accounted for by changing the mixing parameters. In the gamma 5 and gamma 1 states have mixing parameters that have a small effect on dichroic amplitude. So it's not, we know that we're certainly not seeing an effect that's commensurate with this kind of jump. In fact, if you increase the local magnetic moment, the mixing parameters should shift in a certain, there's a definite direction. They should shift towards the mj equals 3 component of gamma 5. And that would give exactly the slight upward tick that we get in dichroism as we cross into the new phase. So these studies were actually done at about 10 Kelvin for this measurement. So we have temperature in these phases. So, okay, so all of that starts to give a picture. Maybe j equals 4, maybe gamma 5, maybe gamma 1. But it's somewhat surface sensitive, and it doesn't. And it's also a little bit myopic because we sort of assume gamma 4 and model it and see aha correspondence. With RIGS, a neat thing is that we can see what's gapped out of the ground state. Where are the other J manifolds that explain the missing degrees of freedom from a single particle picture? In particular, the gamma 4 manifold that I've been talking about takes up 9 of the 15 states for 2 J equals 5/2 single electrons on site. A bunch of the rest are in gamma 2. Well, 5 of the rest are in a gamma 2 symmetry. This is a symmetry for RIGS from the material. Excitation energy is on this axis going up to a couple of eV. Incident energy is the same O-edge range that I was talking about. And this is what we get from an oxidized surface. We get a nice one-to-one correspondence. We see all the J symmetries that we expect in a highly localized picture. Uranium oxide is not insulator, just for the record. So it's getting a localized picture is very reasonable. UO2, which is what we expect to see conversion towards. And we can see this J equals 2 manifold, saying that those states are really taken out of, and you shouldn't think of them as being available for your model. But if we go to a pristine sample, this is now excitation energies on this axis. These states, by the way, come from a silicon resonance that starts right around this curve. So please ignore these states for the moment. I can break down in detail what's going on with them, but they're not very relevant to the story. So this J equals 2 excitation kind of melts, which suggests and becomes very broad, which suggests that maybe maybe some of it is mixing into the ground state. Just not very much, because you can still see that it's there. Anyway, the last thing that we wanted to see is what's going on maybe with crystal field excitations. Can we find them where they haven't been found with neutrons? If you look in this simulation, I've deliberately pushed all the crystal field excitations up to a very high energy. This is cheating, but I just wanted them to be more visible. In the spectrum, you can see that there's something there that kind of matches the instant energy dependence expected for crystal field modes. These features are cleanly resolved from the elastic line. They're actually there. So if we look at the integrated intensity of those low energy features, this dashed curve shows the intensity you expect for crystal field modes, and most of it is actually there in these low energy features that stretch up to 0.3 or so eV. So it seems like we found the crystal field modes, the crystal field mode scattering intensity. It's just the matrix element isn't giving us localized crystal field modes. It's giving us band excitations or something more itinerant, something more complicated. And this is, again, most of the crystal field intensity that we expected to see from our scattering experiment. It doesn't say that there aren't well-defined crystal field states very close to zero energy, because we have 35 MeV resolution as opposed to wave number resolution in the experiments that we've just been hearing about. So here's a breakdown of the J equals 2 manifold. As things become more itinerant, you expect it to melt and the intensity to converge into low energy band excitations. It's not totally melted. In fact, we can fit all of the intensity that's there in the oxidized spectrum in just a broader Wray state. So it seems like it's modified, the J equals 2 states are modified by itinerancy, but they're not getting mixed very much into the ground state. They're still really kept out. And the J equals 5½ modes should be sharp whether it's itinerant or not. Well, 5½ to 7½ excitation looks like a J equals 5 excitation for a local feature. And that does stay there and stay sharp no matter what. So anyway, I'm getting into minutia now. So everything that I really wanted to say, I've already said. Let me get back to it. J equals 4, not much J equals 2, and some constraints on the spinner that can be a part of, on the pseudospin that can be a part of hidden order. And again, we do see the crystal field intensity. It's just spread out over a range that neutrons wouldn't be sensitive to because they want a sharp excitation. That will come up again when I get to my summary slide. If you didn't think that what I said just now was cool, then let me mention that we have a neat new experimental facility that's going to be delivered early next year. We have PLD, PDD, and MBE synthesis chambers attached to the same transfer tunnel, an ARPA system with a small spot and some nice specs. We hope to have SDM, but this is going on the 10th floor in New York, so it's not going to be in downtown Manhattan, so it's not going to be a nice SDM. It's going to be a baby along this one. And this is currently supported by the Moore Foundation here in the NSF. And we want people who do synthesis to apply for the jobs that I was talking about before, because we want to bring in people with a background to make good use of this. This is to some extent a user facility. I and Jason and others, maybe some others here, have been a part of planning and expressing enthusiasm for upcoming synchrotron beamlines that will do great things for rigs. I won't dwell on that too much, except that one is proposing to be the first beamline to have a 100 nanometer beam spot for the rigs technique, which will be fantastic for seeing what's going on in real space. One at the advanced light source should give us 2 orders of magnitude in extra flux and much better resolution. So we're looking forward to that with great excitement, and I leave you with the summary.
So the talk is open for questions.
So I'm curious, because I know Corbin Booth's data was also X-ray absorption spectroscopy, right? So can you explain to me why he says it's 5F3 and you say it's 5F2?
Yes, the difference is 2 numbers, which are 0 and let's say 10. All right, done. Next question. No, so in the VUV, I take a 5d electron and put it into the 5F energy level, or if it's nickel oxide, a non-insulator, I take a 3p and put it into 3d. The principal quantum numbers are whatever. Hartree-Fox says the radial size of the wave functions is almost the same in each of these cases. The effective monopole potential of the core hole is basically 0. If we're looking at, say, nickel oxide, where things are simpler, we see a beautiful picture that looks exactly like it would if you took out the ligands, whether you have the ligands or not, whether you hybridize with oxygen or not. We see exactly the same thing in XAS. Cohen-Ruth's kind of spectroscopy, where you go to the hard X-ray regime and you take a tightly bound electron that's very constrained in space, and whoop, you expand it into the valence level, comes with a core monopole potential that's on the order of 10 eV. And there, you're really interrogating the material and asking, how many d electrons do you have? How many f electrons do you have? And there, if he looks at nickel oxide, he's going to get the answer 8.2 d electrons. He's not going to get the answer, I have a spin 1 degree of freedom, which is what my technique is basically saying. So Corwin is seeing that, yes, valence diverges from 5F, what you expect for 5F2. And when you consider that there are 12, in a 5F2 picture, there are 12 empty uranium orbitals. And if they each mix coherently just a little bit with local states nearby, just on the order of 5%, you're bringing in 0.6 electrons or so. It doesn't take, it's not discriminating between a coherent picture of electrons spending a little bit of time on neighboring atoms and an incoherent picture or a picture where electrons are living on, an extra electron is really living on uranium and participating in the degrees of freedom there. So that's the distinction that I would draw.
Yeah, I think DMFT people would say that in a correlated matter, you can't really say that you have one field shell with 5F2, so you have an ensemble, they're all a field, they're all dancing around, those things need to be accounted, and I think that spectroscopy has not been mapped with that kind of calculation. Mm-hmm. This machinery hasn't been developed. The balance is kind of extracted from non-correlated approach.
I agree completely, which is again why, especially in terms of the amplitude of the effect, or the amplitude of the magnetic moment that you have, which I think needs to be normalized by a factor of 2 for when you go from a local to the picture of the actual system. There are big questions, and I think Moritz Havercourt is specifically looking into that from a theoretical standpoint. I've heard.
Actually, what you said is not true.
Oh.
If you do it there, put up with him.
Yeah.
If you do a DMFT, you do a local approach, right? And if you do X-absorption or whatever technique, you can do the same. You can do a cluster approach, extended cluster approach. You can do that. When you do a transition metal oxides, we take, let's say, iron and manganese before, 5 didn't hold, 6 didn't double hold, just exactly that DMFT can do. Right? It's simply the extent of things. So you can interpret the non-intervalence also in that way. The only thing that is different with uranium, in this case, sometimes you don't do it, but X-absorption is not so sensitive to these other mixed systems because of some spectral wave interference. makes famous that you're going to have. Right? So your technique, if you do X absorption, is more sensitive to symmetry. So even for symmetry, this is what I'm going to do.
Right, it's not, again, it's not pure, it's, again, it's not pure cut because you are taking projections and an effective orbital picture that would make everything simple is only one limit of how you can think about it. From my perspective, that's sort of the answer that I believe in philosophically, but in terms of how it's parsed in the details, I need to confess that I was very recently not so long ago, talking to Gabby Kotler and saying it would be really great if we can get sort of local symmetries from your picture and plug them into as a starting point for our simulation and see what we get there. So it's not, I think theory is still playing a little bit of catch up on the fine details of this.
I wanted to ask you about the ferromagnetism on the surface of samarium boron 6.
Yes.
So does that have a Curie temperature that you can measure, or how big is the moment, or?
So that's observing the ferromagnetism. That's not my paper. Here, this hysteresis in a conductivity measurement is associated with the ferromagnetism, and it's a pretty good argument that there should be something ferromagnetic on the surface. Somewhere around 500 millikelvin, unfortunately. I would love to cool down to 500 millikelvin or lower and measure XMCD on this and sort of try to see the development of it as the surface ages and you get more large moments. But beamlines largely won't do that. The beamlines that have this capability in particular won't do it easily.
So it's not a direct.
Right, it's hysteresis in the Paglioni case, but it's and something that looks like quantized conductivity, which you should get from the surface, but it's not very direct to my knowledge.
Well, if there are no further questions, let's thank Andrew.